Hello, my name is Satish Puthenparail. Welcome to my lectures on groups, rings, and fields. My plan is to cover as much as possible the syllabus of algebra first paper of the MSc course at Calicut and Kannur universities. This is a very elementary course on these algebraic structures, not well advanced at all. The textbook I am going to use for this course is a first course in abstract algebra by J.B. Fralik. There is no prerequisites for this course. Actually, I am going to start from the definition of a group from set theory. Set theory. So, you don't really need a prerequisites to attend this class. So I'm going to start with the definition of a group. So what I'm going to do is I'm going to discuss the motivation behind developing this algebraic structure. So let us take two sets. The first set contains some randomly chosen objects A0, A1, A2 dash dash dash, A minus 1, A minus 2 dash dash dash. I'm going to call the objects like this. It is just an object. We don't know what those objects are. And the second set is all integers 0, 1, 2, 3 dash dash dash, minus 1, minus 2 dash 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 here. We know about the elements of this set. They are numbers, integers. Here we don't know anything about the elements. So here, besides knowing about these numbers, we know that something can be done between the elements. Like you can add two elements. We'll call it as a binary operation. We can perform a binary operation on elements on this set. And that operation we now call it as addition and denoted by plus. What does this binary operation do? Take two elements and give you a single element. For example, 1 plus 2 is equal to 3. So we already know about this. Right now, we don't know we have a binary operation on this set. It is just a randomly chosen objects. But here, we can, as I said, we can talk about a binary operation. And besides this binary operation, there are something else we can do on this set. Let us state a problem here. An element is added to 2 to give 5. This statement is a valid statement with respect to this set, but not here. An element is added to 2 to give 5 because addition is a valid binary operation on this set. Now the question is, what is that element? So what we do, normally we will form an equation, x plus, this is the binary operation defined here, and this is the variable, the value of which we want to find out, plus 2 is equal to 5. So we form the problem here in terms of this binary operation. Then what we do is, this is actually the definition of the problem. Then what we do is, our aim is to find out the value of x. So what we do is, so x plus 2 and 5 are the same element of this set. So what you can do is, you can add 2 more elements here, 1 more element from both sides. So 2 plus minus 2 is equal to 5 plus minus 2. This is possible because this and this are same. Because it's a valid binary operation, it has to give the same number. Then what we do is, we will group them together. This one is equal to 5 plus minus 2. And we'll compute this one. So this is actually x plus 0 equal to 3. So x equal to. So the value of that element is 3. Now, what is happening here from here to here? We want to isolate x. Meaning you should have only x here. The left hand side of the equation, you should have only x. To make just an x, we need to add x plus 0. There is a plus here. So you want to nullify this plus 2. That is why we are adding a minus 2 here. So here, what is the property here? X plus 0 is equal to x. From here to here, x plus 0 equal to x. Meaning this 0 is an element of this set, which when added to any number of the set remains the same. And that kind of number is called the identity. Any number, not necessarily x, any number if you add to 0 will be that number, that element. So in order to, so that was our aim. So there is an identity here. And what would you do to get this 0? We added another number to this. And that is the inverse. So for every element here, there is another element such that if you add together, that will be 0. And before that, what happens? We group this one together. So that is actually the identity. Sorry, that is actually the associativity property. Meaning, when you are adding more than 2 numbers, you can group them in any way you want. with the same order. Otherwise, it is not possible. So, in order to solve this problem, we need these two properties, these three properties. We need an associativity, we need an inverse, we need an identity. And also, it should be a binary operation. So, to solve this is called a linear equation. So, to solve a linear equation like this, what we need is we need a binary operation. Of course, to form the equation itself, we need the binary operation. Then we need an associativity property. Then we need an identity, then inverse. So, if this set would have been like this, without knowing anything about the element, or don't have any properties of this kind, we would not have solved this problem. In fact, we would not have even found this problem here. That is where the definition of group comes in. A set with this property is called a group. So, we will come to a formal definition. So, the formal definition of a group. A group G is a set with is a non-empty set. Is a non-empty set with a binary operation we'll call that star, denoted by G, star having the following properties. The first property is star is closed in G. That means if you take any element, any two elements in G, then A star B belongs to G. Or you can say star is a map from G cross G to G. Second property is that star is associative. That means A comma B comma C belongs to G implies A star B star C equal to A star B star C. Third one is there exists an element E in G such that A belongs to G implies A star E is equal to E star A is equal to A. Meaning for all elements in G, A star E is equal to E star A is equal to A. Fourth property is for every A in G there exists a unique element. Well, we don't want to say unique right now, we'll prove it is unique. There exists an element A inverse such that A times or A binary operation A inverse is equal to A inverse times A is equal to the identity. If these four properties are valid, then G is a group. In addition to this, if A comma B belongs to G implies A star B is equal to B star A, meaning the order in which you are multiplying, you are taking the product with the binary operation is immaterial. Then for all A and B, then G is called an abelian group. Or a commutative group. So we are going to give a lot of examples on groups, but before that we want to establish some properties of inverses and identities. The first and the first property we are going to show is, let G, or we'll say it as, let G comma star be a group and A comma B comma C belongs to G. Then A star B is equal to A star C implies B equal to C. It's called left cancellation. We will make use of only the properties of a group here. So how do you prove this? A star B equal to B, A star C implies A inverse star of A star B is equal to A inverse star of A star C. The property we are going to use here is, these two are same elements. So you are multiplying an element with the same element. And there exists, for every A in G, there exists an A inverse. So here we are using the existence of inverse. Now what we are going to do is, A inverse star of A star B is equal to A inverse star A star C. This is associativity of the group. And this is A inverse star A is equal to E times B is equal to E times C. This is actually existence of identity. And that implies B equal to C, property of identity. So if this is true, then A star B is equal to A star C, then B is equal to C. This is called left cancellation. So the next property we are going to prove is, let G be a group, then identity is unique. Identity of the group is unique. Of G is unique. So what we do is, let E and E prime be two identities of G. So what we can do is, E times E star is equal to, or you can say E prime is equal to, E prime is any number, and you are taking here E as a identity. So E prime is equal to E star E prime, and that is equal to, now you take this as the identity and take this as a general element, and that is equal to E. So that means identity is unique. Third property, let G star be a group, then the inverse of every element is unique. So let A inverse and A inverse 1 are two inverses of A. So what does this mean? This means that A star, A inverse equal to E, and that is equal to A star A inverse 1, because these two are inverses of A. Then now use the first property, left cancellation. This implies A inverse equal to A inverse. Implies the inverse of any element in G is unique. The next property is let G star be a group and A comma B belongs to G. Then A star X equal to B has a unique solution. What we need to do, prove that there is a solution and that is unique. So there are two steps. So this implies A inverse star of A star X equal to A inverse star B. This is possible because you are multiplying with A inverse on both sides. and that implies A inverse star A star x equal to A inverse star B, and that implies E star x is equal to A inverse star B, and that implies x equal to A inverse star B. That implies there exists a solution for A star x equal to B. Second part is we need to show that this is unique. So what we do is let x1 and x2 are two solutions of A star x equal to B, and that implies A star x1 is equal to B is equal to A star x2, and that implies x1 equal to x2. Left cancellation. That means A star x equal to B has a unique solution in Now let us see some examples. The first example is the one we started off with, that is a set of all integers with addition as the binary operation is a group. This is actually countably infinite abelian group. For all the examples I am going to give you, you need to verify the identity and inverse of elements. I am not going to do that. That is an exercise for you. So I am not going to say this is the identity of this group. Okay. Second is the set of rational numbers with the addition is a group, and it's all the same as countably infinite and abelian. Now, third one is R, set of real numbers with C, is a group uncountably infinite abelian, and set of complex numbers is a group uncountably infinite abelian. Now we are going to take an example from geometry. U is equal to the complex numbers such that its norm is 1. This is actually the collection of all points on a unit circle. So it's going to be like this. So all points on this circle. So if we take 2 points, we need to define the binary operation here. So let us take 2 points, Z1 and Z2. So Z1 and Z2 can be expressed as, so binary operation is defined as like this. If Z1 if z1 is equal to e to the power of I theta 1 and z2 is equal to e to the power of I theta 2, then define zeta 1 star zeta 2 is equal to e to the power of I theta 1 plus theta 2. See, any element on this can be written as e to the power of I theta, or is equal to cos theta plus I sin theta. So if you take two elements here, theta 1 and theta 2, then the C1 star 2 is equal to I e to the power of I theta 1 plus theta 2. That is, this angle is going to be theta 1 plus theta 2. That is how it is defined. So this is a uncountably infinite abelian group. The next one is there are also points on the unit circle, but not all the points, only some points. Un is equal to complex numbers such that z to the power of n is equal to 1. So these actually are collections of nth roots of unity. And actually they are cos 2 pi r by n plus I sin 2 pi r by n, where 0 less than or equal to r less than n. Integer. R is an integer. So there are n points here. So this is a finite group with n elements and it is actually abelian. The next example is f is equal to all functions from set of real numbers to set of real numbers is a group under usual addition of functions. So f star is a group. This is actually an uncountably infinite group, abelian group. Definition is actually f1 comma f2 belongs to f, then f1 plus f2 is equal to of x is equal to f1 of x plus f2 of x. Next one is the collection of m by n matrix from entries from real numbers. The collection of all m by n matrices with real entries is a group under matrix addition. So find out identity inverse and also show that the binary operation is closed. Next one is M and R, the collection of all n by n matrices with real entries is not a group under matrix multiplication, because zero element of M and R does not have inverse. And how do you make this a group? The GLN of R, normally we write it as GLN of R, the collection of all n by n invertible matrices. Is a group under matrix multiplication. Now, we already found one, but the formal definition of a finite group goes like this. A group, if a group contains only a finite number of elements, it's called a finite group. A group G is finite if it has a finite number of elements. The order of a finite group is the number of elements in the group, and is denoted by G. Examples. Common example is actually just one element is a finite group. This is the simplest finite group. The addition or multiplication or the binary operation is the element itself. So inverse, identity, everything is same. By the way, if it's a finite group, we can form a table of binary operations. Can write it as E A1 A2 dash dash AN E A1 dash dash AN, and you can fill up the rows and columns here. So you can physically define the binary operation. You don't need to have a rule to define it. Another example, a common example is Zn. That is actually 0, 1, 2 dash dash n minus 1 with the addition modulo n. For example, Z2 Z2 is equal to 0, 1. And if you write the binary operation table, it will be 0, 1, 0, 1. Here 0, 1, 1, 0. 1 plus 1 is equal to 2, mod 2 is 0. And 0, 3 is equal to 0, 1, 2. This is mod 2, this is mod 2. And also you found one un is c in complex number, c to the power of n is equal to 1. This is also a finite set. So you can say here the order of un